Our next speaker is Tom Potter from Crescent, who works as a computational chemist.
Okay, thank you. And thanks for the invitation to talk at this conference. I'm going to be talking a bit about the work I've been doing at improving the efficiency of FEP calculations by the use of truncated protein models. So I think, as we all know at this conference, FEP, while it is a very accurate method, can also be very computationally expensive. And particularly in the cases where we're looking at large proteins, we're spending a lot of time simulating the motions of residues which are possibly not very, possibly don't contribute very much to the binding free energy of your ligand. So we were kind of interested in whether there's a possible way we can kind of modify the way we kind of model the protein to kind of reduce this kind of aspect of the computational cost. So there are kind of a few different ways that people have kind of looked to do this. So for example, you could do something involving coarse graining, although the kind of methods for doing that for protein ligand systems are possibly not quite there yet for getting accurate results. There are kind of some examples of people using kind of local sampling methods. So, you know, you might simulate the inner bit of the active site while kind of freezing the outer bit of the protein. So this is quite a nice example of that in this publication here. And then there are kind of methods for just truncating the model of the protein. So again, this isn't a new idea. There are a few examples of this in the literature. A couple of papers by this group here, looking at, first of all, non-periodic systems, so just kind of a simple spherical model of the protein, which only includes some of the active site, some of the protein. There were kind of other examples of this in this conference, which seemed to work pretty well. But we were actually interested in whether we could do something on a periodic truncated protein model. And again, there was an example of this in the literature where it was found that although this can work, there are issues with the way you have to restrain the outer residues, which can cause errors in the simulations. So just to kind of briefly give a bit of background on Flare FEP, which is kind of what we're trying to add to with this project. It's a robust and user-friendly FEP package, which is integrated into the Flare molecular modeling package. And that allows you to kind of run FEP while benefiting from the kind of protein and ligand preparation tools that are present within Flare. And we have some kind of nice features like adaptive lambda scheduling and kind of automatic graph generation using LowMap, including kind of automatic intermediate generation, as well as some kind of nice kind of analysis methods for looking at the results of FEP calculations. So we basically wanted a method that we could kind of integrate into Flare FEP that will allow our users to run the simulations more quickly and efficiently. So basically, what I kind of did when I was doing this project was, first of all, took a bit of a look at the different restraint schemes that you could potentially use on these truncated protein models and see how they affect the results of free energy calculations. And then kind of do some bigger benchmarks to see, okay, how does this work when you look at kind of full data sets of various types, including some more difficult systems like GPCRs. And then, obviously, importantly, see how much faster does this actually make the FEP calculation. So the general procedure for doing this is pretty simple. You take a protein ligand system that has been kind of carefully set up and parameterized, in this case using the Flare tools, and you truncate it like this. So you define an outer cutoff. In this case, we're using 15 angstroms from the ligand, and then you truncate the protein at that point. So you remove all of the residues outside of that kind of spherical cutoff. And then after you've done that, you kind of cap all of the new termini that you've introduced with kind of neutral capping groups. Then you add some sort of restraining scheme, which I'll discuss in the next few slides. And then you run your FEP calculation as normal. So first of all, we looked at using position restraints and various different schemes for doing this. First of all, you can define an inner cutoff. So in this case, we're using 12 angstroms, so that gives you kind of a 3 angstrom restrained zone within at the outside of the truncated model. And you can, first of all, restrain all of the heavy atoms within that zone, which is the most restrictive method that we looked at. You can restrain only the alpha carbons within that zone, or you can actually only restrain the atoms in the capping residues that you've added when you did the truncation. So we kind of tested that in an initial kind of quite small set of links from the CDK2 data set, just to see kind of how the different restraining procedures behaved. So we're looking at these 6 links, and we're looking at those 3 ways of restraining the protein, as well as the unrestrained truncated model. And we're comparing the delta-delta Gs from those simulations to the ones from the full protein FEP calculation. And actually, in this case, the best truncated model was the unrestrained truncated protein, which we found quite interesting, and it kind of confirms to us that by adding these position restraints, you are restricting the motion of the protein enough to affect the FEP results. And in some cases, it's, the difference is pretty small, but in some cases, you get quite a big difference depending on which atoms you restrain. And essentially what we think is happening here is that by restraining the outer residues, you're also restricting the movement of the residues in the inside of the active site. And that is kind of going on to affect the movement of the protein itself, the ligand itself. So if we look at this example, which is, I think, taken from the ligand 21 from this data set, if you restrain all of the heavy atoms and you look at the ligand RMSD from one of these simulations, you're essentially only sampling 1 conformation. Whereas if you do no position restraints, you are then able to sample 2 conformations. And that is kind of consistent across a number of replicas of this ligand from different transformations involving the ligand. So I then kind of went ahead to look at whether there's a different way you can do this, and I did this using distance restraints. So the way this was implemented is that if you see this model of the protein here, I've highlighted the capping residues, and we're applying flat bottom distance restraints between essentially the closest pairs of those capping residues. And we're rather than just doing a harmonic potential, as I say, we're doing a flat bottom potential, and the minimum and maximum distances for that flat bottom potential is taken from a short dynamics run of each ligand. So we simulate all of the ligands in the system in turn for 5 nanoseconds. We combine all of those trajectories, and then we take the minimum and maximum distances for all of these pairs that I'm highlighting here, and we kind of apply those as the distance restraints. The idea here is not to kind of restrict it to exactly the same distribution as the whole protein, but it's to make sure that any kind of any kind of configuration that you can get in the whole protein is also permissible in the truncated protein, and that kind of addresses some of the issues we saw before. And if you look at the results for this set of 6 ligands, you can see that in the kind of the red bars, the results do improve, and they're now much more comparable to the unrestrained protein. So I should mention that although we do need to apply restraints essentially just in case those disjointed chains we've introduced try to fall apart. Actually, in practice, over the timescale of these MD simulations, they tend not to. So the distance restraints are kind of largely there as a precaution, and that kind of explains, I guess, why adding the distance restraints and having no restraints whatsoever can give pretty similar results. So we then kind of went on and did some bigger benchmarks on this distance restraint method. on a few different protein data sets. And just to briefly describe the computational details of this, we did all of the kind of adaptive lambda scheduling and the graph generation automatically using Flare without any sort of kind of manual intervention. So this is essentially the out-of-the-box Flare results. And we compared whole protein simulations that were run within Flare version 7 to truncated simulations that were run with SOMD free energy directly. SOMD free energy is the free energy simulation backend we use from OpenBioSim. And we're using kind of the default simulation length that's within Flare FEP, which is a very short 200 picosecond restraint equilibration, followed by 4 nanosecond production for each lambda window. And we're using Amber and OpenFF Sage to do the simulations. So I kind of started off by doing this on 4 different proteins. So first of all, CDK2 and base. And in all of these plots, I'm showing the whole protein benchmark with Flare 7, the truncated protein result for the same system using reaction field electrostatics, which is what was kind of the default within Flare 7, and then looking to see what happens when you use the kind of the more accurate PME electrostatics for the truncated model. So essentially, although we don't get exactly the same result when we do the whole protein simulation versus the truncated protein simulation, but if you look at the statistics overall, we are kind of, depending on the system you look at, you're kind of seeing maybe a bit of a reduction in R squared, and often a bit of an increase in the MUE, but the MUs are still kind of fairly good, so kind of below kind of 1 kcal per mole. And it's kind of a similar story for TIC2 and P38. Obviously, P38 is generally much more noisy than TIC2. So we are seeing that for some proteins, the change you get when you do the truncation is much bigger than others. So if you look at the TIC2 stats, they're all fairly similar. If you look at P38, the change is a bit bigger, particularly when you look at the R squared. But again, especially when you look at the PME results, the actual stats for these FEP calculations using the truncated model are fairly good. So for this sort of system, you can kind of see the utility of doing this if you have a very large set of ligands where you might want to kind of improve the computational efficiency. And then potentially on a smaller data set, do your full protein FEP in kind of a more accurate manner. So just to kind of highlight the actual level of speed up we're getting with these, obviously none of these proteins are massive, but we are, particularly for CDK2 and P38, we are getting a decent speed up in the simulations. These are the kind of relative speed up for the bound leg of the FEP calculation, I should say. So obviously it's system dependent, so for smaller proteins like base and TIC2, you're not getting as much of a speed up. So there's going to be kind of a system-by-system decision-making process depending on the size of the system and maybe some benchmarking whether you actually want to do this for your project. And just to kind of finish off by looking at membrane proteins. So this is something that's going to be a bit more of a challenging case for truncation, because obviously membrane proteins are much bigger, and actually the membrane itself, although it's quite far away from the active site, is important to the behavior of the protein and the ligand. So really, kind of just to see what happened, I applied the truncation procedure anyway, just to kind of see what the results would look like. And basically what I did initially was to do the truncation and remove all of the lipids from the system. The reason I removed all of the lipids is that if you keep some of the lipids within that truncation sphere, you then have to worry about how you restrain them while still keeping the behavior of those lipids kind of reasonably correct, and without introducing artifacts to the actual movement of the proteins themselves. And what I found when I did some initial tests doing that, doing kind of that procedure of keeping the lipids and doing some restraints, was that it actually degraded performance rather than improved it over the simulations with no lipids. So if we look at this first test case of A2A, you can see that kind of perhaps unsurprisingly, the kind of errors you introduce by doing the truncation are a bit bigger than you would see when you do the truncation on some kind of non-membrane proteins. So we see kind of a fairly substantial decrease in R squared and a bit of an increase in MUE. But actually, when you switch to the more kind of accurate electrostatics, again, the results look pretty good. And kind of if you were to kind of just do that simulation as your benchmarking, you would probably say that's a reasonable benchmark for a membrane protein. And again, I looked at a couple of other systems as well. So first of all, P2Y1 and OX2. So again, these are a little bit messier than some of the other systems I've looked at as well. P2Y1 is a bit of an interesting case because we're looking at a lipid-exposed binding site. So we're applying this same truncation procedure where we remove all the lipids, but on a system which has a lipid-exposed binding site, which, to be honest, I didn't expect to give particularly good results. But actually, if you look at the benchmarks, the results look pretty good. I wouldn't take this as proof that you can do this for any lipid-exposed binding site, obviously. Again, for this sort of system, if you want to do something like this, you have to do very careful benchmarking to check that it is actually going to work properly. But in this case, it doesn't seem to be too bad. And then for OX2, again, overall, the results look pretty good, although there are actually in the whole protein and the truncated benchmarks, there are some fairly big outliers that I don't think we fully understand yet. But overall, the kind of results look, again, kind of with an MUE of kind of less than 1 kcal per mole and a reasonable R squared value, although it's a bit lower for this case here. So kind of the key thing about the GPCR results is that although you do see a bigger change in the results when you do the truncation, you also see kind of a comparably bigger speed up. And that's kind of the trade-off here, really. So depending on the system and depending on essentially the size of the membrane that you've added, which is basically relies on kind of the OpenMM solvation code at the moment, you can get anything between kind of, well, in this case, 85% to about 355% speed up. So again, as I say, provided you kind of do a little bit of benchmarking to make sure it works for your system, this is something that could be quite useful if you have a very large set of ligands and a large membrane protein to kind of narrow down the ligands you might want to do in a more accurate, a more accurate kind of whole protein study with the full membrane in place. So yeah, that's pretty much all I have to say. Kind of shown some initial results that show that truncation can give you good results while speeding up the simulations in many cases, although there will be kind of cases where it works better and cases where it works worse, and that's going to be quite system dependent. And the use of distance restraints seems to be beneficial over using position restraints to kind of restrain those outer residues of the truncated protein. And we can see that in some cases, at least, this also works for membrane proteins, even when you kind of remove the lipids from the system. And kind of just to say that this method is kind of planned to be included in a future release of Flare FEP, so kind of people can try it out themselves on their systems. And yeah, finally, just to kind of thank people. Firstly, the people at Crescit who did the whole protein benchmarks in Flare 7, and also the people at OpenBioSim who kind of worked on implementing those restraints within SOMD free energy, which was kind of crucial to this project. And just to kind of briefly plug this Crescit user group meeting, which is happening in Brussels next month on the 18th and 19th of June, if anyone's interested in that. And yeah, thanks for your attention, and happy to take any questions.
Hi, so very nice talk. So I was under the impression that people use reaction field because it is much faster than PME, and in your speed up table, it seems that reaction field is not like a lot significantly faster than PME.
Yeah.
And also, you use reaction field on membrane protein, which makes me very uncomfortable.
Yeah. So basically, this kind of PME versus reaction field speed up seems to be GPU dependent from what I've seen. So I initially did some benchmarks on some older kind of 1080 GPUs and found that actually the speed up, kind of the slowdown on using PME was kind of 20-25%. But actually, if you use the newer GPUs with OpenMM or OpenBiosim's wrapper for OpenMM rather, it goes down to a few percent. So possibly there are some optimizations there that have kind of closed that gap between the two electrostatics methods.
Hi. Thanks for this nice overview of the sort of the setup of FEP capabilities at Crescent. The A2A and OX2 sets, if I understood from the blog and also the LinkedIn post discussion, I didn't see your slides, but these are the same sets that we worked on with Janssen and that Francesca presented yesterday, right?
Yeah.
I think. Did you also? I mean, appreciate that the set was slightly adapted by the Schrödinger team, and did you also look at the small sort of the sub-series or the kind of predictions with the different settings that Francesca showed yesterday?
No, we haven't yet.
Okay.
So I think as far as the kind of whole protein membrane benchmarks go, at the moment we've kind of only done the kind of flare out of the box. We are looking to, I guess, do some kind of more detailed ones, but yeah.
So it will be interesting to see that stuff really prepared.
Thank you, Tom. Very nice talk, and I'm very fan of truncated systems. So we've been doing this in Q for around 30 years, and but in a different way. And I would like to see a bit your thoughts here, because you're truncated the system and then using PME, which might get to some artificial symmetry there on your PME on such small systems. What is, in your sense, the difference between this and the finite aperiodical systems like spherical boundary conditions that was presented yesterday?
So I think so the reason we want to do this in a kind of a periodic system is that then allows us to use PME, which is required for kind of things like charge change, FEP, at least in our implementation, and kind of GCMC. So yeah, I think that's kind of our thought behind doing that. But I take your point that using PME, but then, which is more accurate for the long-range interactions, but then kind of making those long-range residues different to what you would kind of expect can introduce artifacts. Yeah. So yeah, that is definitely a potential source of error in these simulations. Yeah.
All right, let's thank our speaker again.